Yeah, it seems to be turned on, right? Okay. So first of all, let me thank the organizer for the kind invitation and this opportunity. It's a great place for many reasons, but for me, in addition, it retains a huge sentimental value, as I spent here 2 enjoyable, memorable years, about, I'm afraid to say, some 23 years ago. So another thing I wanted to say is this is a course for graduate students, and my understanding is I'm supposed to give grades. So I will be, in the course of these lectures, I will be assigning problems. And the expectation is the interested graduate students are expected to solve as many of them as they find appropriate and then turn in for grading. If needed, let me know, and I'll try to, probably I'll do it anyway, I'll try to prepare the written notes, not of the lectures, but written formulations of the problem so as to make it easier for you. At the beginning of the course will be especially elementary, so there will be especially many problems because there is a cheap way of assigning, of making problems if you lecture on standard material, just to meet more subtle parts of the proofs and ask people to fill out the details. And I'm afraid I will overuse this opportunity. But on the other hand, it is definitely true that if you are not very familiar with this and are interested, the best way to learn this is, of course, to do these problems. So this said, let me begin. So I will be talking about algebras of Chiral differential operators. In one sentence, an algebra of a Chiral algebra of differential operators, or an algebra of Chiral differential operators, that's the notation that will appear on the board sometime later, is to, so X is like, you know, a smooth variety. So it is to the corresponding G scheme what the usual, so ordinary algebra of differential operators is to X. So this is a slogan to be explained later. So this is a non-trivial infinite dimensional generalization. For this is a sheaf of, this is an associative algebra. And this is a sheaf of vertex algebras. That perhaps is the most non-trivial part. In what way it's a non-trivial generalization. More technical issue is that while this is a sheaf on X, so here you would expect this to be a sheaf on the jet scheme. It is not. So it's also a sheaf on X itself. Morally, it's defined on the jet scheme, but technically not. There is, in fact, a generalization of this algebra, more or less straightforward, going under the name of H-adic algebra of Chiral differential operators, and that will live on Gx. This is due to our joint work with Mayuki and Toshiro, but I will not be speaking about it. So I will spend considerable part of my lectures explaining about this thing. And so this is the part which is, of course, should be regarded as common knowledge, and where unjudiciously remaining in the room professors will get bored down to death very quickly. And this is where I will start. So usual ordinary differential operators. So we all know. So what is a differential operator? Everybody knows what that is. It's an expression like this. I will spend a considerable part of today's lecture on clarifying this, obscuring this matter as thoroughly as possible. So, what is a differential? So, C will always be the ground field, although as far as I can see, if you replace it with any characteristic 0, perhaps algebraically closed a field, there will be no difference. And typically, today at least, and most of the time, I will be dealing with a C algebra A. So what is an order A differential operator, so to say, on A? This is as follows. First of all, consider the space of linear over C and the morphisms of A. A is a vector space, so that's an associative algebra over C as well. An order K differential operator is an element of this algebra, such that if you bracket it with arbitrary K elements of the ring, the result is 0. So for any F1, Fk elements of A. Of course, I think of A as an algebra of functions on a, say, affine variety. Hence my notation F. In this, probably this formula is self-explanatory, but just in case I'll write that in this formula, F, whatever index is, means the operator of multiplication by F. That is a map from A to A that sends an element A to F times A. And the bracket means the usual bracket. That's an associative algebra, so operators can be composed. And that's what the bracket means. All right, now first of all, let me introduce the notation. I will let B sub A super K be the set of all order K differential operators. So here is a list of observations / exercise. So let's try to learn how to work with this. Let's develop a few for that first. So what's an order 0 differential operator? Well, it's naturally isomorphic to the ring itself. And the map is as follows. It sends an operator P to its value on the identity. And I will typically write just like this, but all my identities will be identified typically. So this is that. Yeah, it's a unit, not just a CL, unit of CL. And not just Prof. I apologize, commutative associative, of course. Next, given an algebra, you can always consider its derivations. So introduce another important object, T sub A. That's the set of all derivations of A. Of course, it's a side remark. It's an A module, of course, and it's a Lie algebra with respect to the bracket I discussed. By the way, should you have any questions, please interrupt me and answer them. If you don't understand the answer, please force me to do a better job of this. I beg you. All right. So that's an operator. So it's part of the entire algebra. In fact, it sits inside differential operators for the one. Do you want me to remind you of the definition of a derivation? This is a notion that will be omnipresent today. Fine? All right. 3. Somewhat surprisingly, and why surprisingly, that will become clear later. In fact, there is a map in the opposite direction. In fact, there is a map from this case to derivations which can be included into the following short exact sequence. A. As we discussed, A is D0. D0, this is an increasing filtration, of course. I forgot to mention it, but of course. So D0 lives inside D1. Hence this map. And now I claim that there is a map such that this sequence is exact. In item 2, we constructed the map in the opposite direction, which splits this sequence. So this is a second observation. The definition of this map is as follows. An element P goes to the map that sends A to the bracket. It's a common story that bracket intends to be derivation. So that's what's supposed to be done. And you're left with the task of verifying the details. So it's a general observation. Combining 2 and 3, we have a canonical splitting. The first filtered component is a direct sum of functions and derivations. Next. So these are subspaces of the space of all endomorphisms, and so they can be composed. So the claim here is that the composition of the ith and the jth component belongs to the component number I plus j. Finally, 5. Once you can compose, you can swap the summand. So there is a map, the bracket. Allow myself to be informal. So just the bracket of the ith component and the jth component. Of course, it's a set. That the meaning of the just as it was there. That's the set of all brackets of elements from here and here. On general grounds, as established previously, it's an element of this component. But in fact, it the computer kind of collapses and lands in I plus j minus 1. All right, so all these properties you're advised to think about and verify allows us to conclude, in particular, there was more than that, but in particular, if we let D sub A to be a union of those, and this is a filtered associative unit of algebra such that I chose not to give you a formal definition of a filtered associative algebra. If you insist, I will. I hope this is clear. That's what 4 claims. Whenever I have a filtered associative algebra, you can consider the corresponding graded object. Which, by definition, is the direct sum of the successive quotients. Now, this canonically an associative algebra. That the operation is defined by choosing representatives. Verifiable of this sounds unfamiliar. And the point of 5 is that this algebra is commutative. It's a simple fact, but one of great importance. Any questions? All right. What does this algebra look like? In general, it's a tricky question. And I'll show you an interesting example. Elementary and interesting. But it is what I am trying to unclarify in the situation when, so that kind of second item in my exposition. So things considerably simplify when A is smooth. I'm not sure there is a formally established notion of a smooth algebra. And if there is, it's probably not what I need. Of course, I'm thinking of a local model for a smooth algebraic variety. So when I say smooth, what I mean, that's the definition for the purposes of these lectures, is that the corresponding module of scalar differentials is a finite rank free a module. Do you want me to remind you what omega sub A is? Omega, yeah, okay. So when you write f of x dx, something that calculus students deal with, is an element of the string. And the algebraic definition is omega A is the free A module on generators. It's just a symbol at the moment. The A for all A in A. Modulo the relations. The most important one is that the relation that models the Leibniz rule. It should also, of course, be linear. Is there anything else?
C-linearity.
C-linear, all right. So alpha, beta, elements of C. One particular point where this is important is that essentially, by definition, if that's new, I really believe that this is something that's not really new, but if it is, if you want to recollect, the algebra of derivations is the same as the space of A linear homomorphisms from omega A to thanks to this relation. All right, so suppose this is the assumption. Then the fundamental just erasing exactly what I may have wanted to remind you about. So anyway, the lemma says that there is a canonical isomorphism. So if A is smooth, as I said, then the graded object is canonically isomorphic to the symmetric algebra over A of the module of derivation. This is a general symmetric algebra over A of defined for any A module. So what it means is the direct sum A plus T sub A plus the second symmetric square plus etc. For example, the symmetric square means the the clash of T. I wanted to say the tensor square, but it will clash with T. I don't know how to denote it better. Tensor square over A, of course. A modulo the action of the symmetric group. So you identify quotient out elements like this. Or, since we're in characteristic 0, it's the same thing as of course the symmetric group on two symbols X there by swapping, and you take symmetric tensors. This is a free A algebra generated by the A module T sub A. The standard fact, of course, here is a proof. We already established that T itself, as well as A, lies inside. Actually, it equals. So that gives you the embedding of the beginning of the algebra. Given this, there arises quite canonically the algebra map from the symmetric algebra to the graded objects. Do you want me to explain that? This is you see, we discussed that this is commutative. And this is a free commutative algebra on T sub A. So if you know where T goes, then automatically, for free, you get where the symmetric algebra goes. Agreed? All right. So we want to show that this is an isomorphism. So what we want is the map in the opposite direction. Ultimately, the argument will be inductive. I begin by observing that there is a map from the ith filtered component to the space of C-linear morphisms from A to component number I minus 1. The map is defined like this. If you pick an element P, then it goes to the map that sends A to, can you guess? Question to graduate students. Given P and A, how would you make an element of degree I minus 1, less than that by 1? All right. Everybody fails. So A goes to the bracket. P and A. That's the whole point. It's very natural. All this, this algebra is all about bracketing with functions. That's built in the definition. That's, this map is exactly another way of defining these components. All right. That's almost what we want, as you will see, but not quite. We have to somewhat improve it. Or rather, this is still too complicated a map. We want to have a map, we want to start with the symmetric algebra rather than this complicated thing. In order to do that, well, it's a standard discussion here. So inside di, there is di minus 1. And this map can be restricted to the subspace. What the image will be. If you give this thing a thought, you will immediately guess. You see, this space has an obvious subspace, just as di minus 1 contains di minus 2. And so maps from A there that actually land here is a subspace. And an obvious observation is that this composition factors, this composition actually has, takes values here. So this same map gives you this commutative diagram. Right, agreed? Therefore, and that's what we will use. We get a map. I will call it phi.
Why the second home space is over A?
What is home over A?
After, so the first home space is home.
No, it's over C.
Yeah, the second one.
Ah, oh, it's a typo. Okay, thank you. Of course. All right, so this, if I pass the quotients, I get a map from the successive quotient to the space of maps from A to the previous successive quotient. So, claim if I pick a P, then there are too many. Phi is depends on the element there, but the result is a function that depends on A. So, given phi on P will be denoted like this. So that's the element there, and my claim is that this element is a derivation. Do you want me to define something here? You should. This is not a derivation in the set in the sense that TA is a space of derivation. It's not a map from A to A. It's a map from A to an A module. But there is a generalization of the notion of derivation from an algebra to a module of this algebra. And a formal definition is undistinguishable from the usual one on the face of it. It's just that the meaning is slightly different. So being a derivation means that the value on the product is exactly what you would expect if you don't think about the meaning of this formula. Except that now, what previously in this case was the product in A now is the action. So this is an element of that module, and this is not the product, this is the action. As well as this. All right, so I have actually a map from the quotient to the space of derivation from A to the quotient. Now remember, the space of derivations from A to A was the same as the space of homomorphisms from the Chiral differentials to A. The same is true in general. And it's true for exactly the same reason. If you start, if you're fine about this one, and this is valid to exactly the same extent this one is. If you write a proof, you won't notice much difference. So this is canonical isomorphic to the space of A morphisms from omega to that module in question. Any questions? So what assumptions have we used so far? None, except those made at the very beginning. So this is always true. It's only at this point that I will use smoothness. In two ways. First of all, I will assume by induction that this has already been identified with the I minus first symmetric power of the algebra of derivations. If you want to study it, of course, start with the very first step. So suppose I is 2. I guess that's the first Yeah, 2 is the first non-trivial. If you want to study this proof, do it first for I equals 10. You will see what happens. All right. That, of course, is a fake use of the smooth. It's just inductive assumption. The whole point is this is free. So therefore, this is identified with a TA, free or finite rank. So this is the tensor product with TA. And so my map is di minus 1 to TA Si minus 1a. Are we done as far as the induction step goes? We wanted what? Having this for Ci minus 1 to get it for Si minus 1, to get it for Si. That's not quite Si, it's bigger. That's in the sense, if you want to study it, the first thing you'll have to do is to convince, to see the difference between this and Si. What there is, though, is a natural map. Remember, this is an algebra, so, and this is S1. So there is multiplication. And that's the guy. So exercise. So verify that this map is the inverse to the map in the obvious map in the opposite direction I started with. Kind of hint, not so much hint as the observation. So the whole point of this discussion is to see that the image of this map lands, I'm afraid what I will say perhaps is not quite correct. It essentially means that the image is not just the tensor algebra, but rather the symmetric part of the corresponding if you embed this into the I minus first symmetric power, then this will essentially belong to the symmetric part of the I tensor power. So think about it. That's an exercise. Any questions? So one conclusion, this is of course all important conclusion, is that A smooth implies the algebra of differential operators is generated by the vector field. And this, we haven't wasted our time. It's not that in a specific case we proved something that is usually valid. It is not. In a sense, this is the whole point of smoothness. Not that I'm formulating a result like that, but it's very specific. This feature is a specific feature of smoothness. Here is a perhaps more interesting than most of my exercises are more interesting ones. So the last statement is not always true. So example exercise. So let A be the space of functions, so to say, on fat point. So take the ring of polynomials in one variable and quotient out the ideal generated by x to the nth. That's an n-dimensional space, right? So the linear, C-linear endomorphism of it is like gelatin. And it canonically contains the algebra of differential operators. Prove that this map is actually an isomorphism. In particular, find the vector field and verify that dA is not generated by the derivations. It's an interesting example, and it's related to some more recent work on Chiral differential operators, but I won't have time to speak about it. Right, any questions? All right, perhaps appropriate at this point to make a digression. We people who like vertex algebras are often perceived by the rest of the mathematical community as physicists. So I'm trying to explain that what we are doing is we're trying to quantize something. And this is the first way towards this claim. So I'll make a digression. Let me talk about Poisson algebra. Should I define this? What Poisson algebra is? Yes or no? Maybe yes. Yeah. That they never respond. Yeah, I know you will, so that's my way of dealing with it. Please. Okay. It's a tiny step, by the way, towards the definition of like vertex algebra. Vertex algebra is a vector space with infinitely many multiplications. Poisson algebra, P, is a vector space with 2 multiplications. And judging by the notation, you can easily guess what I'm about to say. With respect to this operation, P is associative and, in fact, commutative, unital. And with respect to this one, it's a Lie algebra. And the two structures are compatible. So compatibility. So the bracket is satisfies the Leibniz. So the bracket of A with BC is C times the bracket of A and B plus B times the bracket of A and C. Here is the source. Of Poisson algebra. I'm cheating, of course. Poisson algebras naturally arise in classical mechanics. But for an algebraist, a source is as follows. So suppose Q is an associative filter algebra. Since it's filtered, you can introduce, as we've done, probably you already see what I'm about to say. We can introduce the corresponding graded algebra. So the assumption, it's always true, but the assumption is that the graded object is commutative. It's half of the structure of the Poisson algebra. The point is that in this case, another half comes for free. So in fact, the graded object is canonically Poisson. And that is as follows. We define, so this of course is a direct filtered means these are the components, so this is just as above, of course. And so we define the bracket that sends the ith component times the jth. To the component number I plus j minus 1. By picking, the solution is of course made by picking representatives. So elements, I don't know, P, so that the bracket of K and Q is defined to be. So P is there, Q is there, you pick a representative, an element of the numerator. So I'll put a hat to signify this. Likewise Q, and then I take the bracket. So on general ground, it lands in the component I plus j. But we have the commutativity assumption, so it actually lands in this component. And that's that. So it's this element modulo apparently. And so the exercise would be to verify that it is, I mean, the graded object is indeed Poisson. The reason is practically obvious. It's Poisson just because it is a general fact that whatever associative algebra you have, the bracket defines a Lie algebra structure on it. So that the Jacobi identity is not worth even talking about, and then it's not hard to see that the Leibniz rule is also valid. All right, so here is the promised statement. So yeah. So the terminology. So we traveled the obvious direction. Given a special kind of algebra, you get a Poisson algebra. Somewhat a bit of demagoguery sounding statement is as follows. In this situation, P is called quantization of the graded object. the content of that, it sounds silly, of course. What happens in reality is that you have this, and to quantize it means to find an algebra such that the graded object is what you had at the beginning. And this is hard. But this is the easy direction that we have so far traveled. So to conclude, the algebra I discussed at such lengths, dA, is then a quantization of, if A is smooth, is a quantization of the graded object, which we computed to the fact that it is a symmetric algebra.
So you should write Q is a quantization of Chiral Q, right? Yeah, P.
Oh, right, yeah. Thank you. I changed from P to Q and page. No, wait a second. There is a. Well, it doesn't matter. This is as wrong as the both ways of stating it are equally wrong, as you see. So, thank you for obstructing the smooth course of my lecture. And yeah, you know what happened. There is a P and Q. And it doesn't make sense to say that P is a quantization of. Anyway, it's so ridiculous. Anyway, so. In view of this, D is a quantization of this algebra. Just as I said, as stated, it's silly, but even in this particular case, you immediately see what the actual quantization is for this algebra. Forget about this one. We would have seen it at the very beginning. This is canonically possible. No matter what, this algebra is very easily made into a Poisson algebra because of the fundamental observation. The Lie bracket of vector field makes the space of vector fields a Lie algebra. So PA is a Lie algebra with respect to the Lie bracket, which the Lie bracket, which is extended to the entire algebra. The algebra is free, so if you know how something operates on generators, you immediately extend it to the algebra itself by using the Leibniz. That was very easy. And so my lengthy discussion really is a proof of the fact that this algebra can be quantized. Here is exactly how. And this is non-trivial because this is only true, not quite trivial at least, because this is true only under the smoothness assumption. So for example, look at that example of the fat point. It's not a quantization of the corresponding, there is the algebra of derivations in the case of the fat point, but that's not the quantization of that algebra. This is an indication of the fact that things are not obvious in the case of a variety with singularities. You know what, it's not half of my time, but it is probably a natural point to make a break. So, what, 15 minutes we're good, or 20? 15. So, in 15 minutes.
So, here in your example, we have this obvious nilpotent element, which causes some effects.
Yes.
If we start with an algebra which is integral, in the sense of being reduced and irreducible, is it then true that the dA is always generated by TA, or is it still wrong?
I think it's still wrong. I really think that, I'm not sure there is a theorem that A is smooth if and only if dA is generated by vector fields, but I think that if typically if there is if your variety is reduced but singular, there is no reason to believe that. Yeah, I think, I mean, perhaps even an example like this will immediately, something like a cross. This is, you mean perhaps irreducible as well?
Yes.
So honest answer is I don't know. Maybe, I'm not sure.
Because if this goes wrong, then a nodal curve might also go wrong, even though it's irreducible.
So you probably understand this better than I do. I'm not an algebraic geometer. I'm not sure. But what definitely is true is that the algebra of differential operators, whether or not generated by vector fields, is not the right object for singular variety. So for example, people doing demodules, in the case of singular but otherwise excellent variety, define the category of demodules not as a category of modules over D on this variety. It really is fundamental. So let me try quickly to finish all of this and then show you an interesting example. So now I would like to show you how this can be made into a sheaf. Localizing differential operator. So let me to begin with assume that A is smooth as above, although what I'm about to say can be generalized. But in any case, suppose A is smooth and suppose you take F in A, which is not nilpotent. Then the following is true. That there is a, so we would like to compare so A sub F as usually is a localization of A with by F. So we would like to compare this algebra with this thing, which perhaps not quite an algebra as it stands. It's clear, by the way, that D sub A is a bimodule. I could have equally used the right A module structure. It's easy to verify from definition that this is canonically isomorphic to this. The point I'm trying to make is that this algebra is canonically isomorphic to that, at least naturally. Why is that? Notice that as written, this is not obviously an algebra at all. So there is something to figure out. And so suppose we want to make a map from the right-hand side to the left-hand side. Well, these are differential operators after all. So at least we then need to be able to map this algebra to this. And so the question boils down to really kind of a sort of calculus type of question. How do you differentiate the quotient rule, for example? What's the derivative of 1 on F? That's in essence our question. So to make sense out of a differential operator as an operator on functions with poles, the question is how do you compute P of 1 on F, or more generally, G on F? And here is a prescription from which, for example, the famous quotient rule, ratio rule from calculus follows. So all right, so we of course don't know what that is. But we can perhaps, we do know what this is. And this can be written as E of f times G on f. And now we know how to swap P and f. Think of f as the operator of multiplication by f. So this equals f P of G divided by f plus the bracket of P and f. You must have observed I'm doing it, kind of wearing the hat of a physicist now. I'm computing without having a definition. So this, of course, is not neither this nor this is known. But now I'm doing an induction by the degree of a differential operator. If the degree of P is 0, now this is a function, and multiply, we know what does it mean to multiply a fraction by a function. The first situation when this is not, some of the terms are not defined, is when P is a derivation. In this case, this is a function, so this term is known to us. This still isn't, but now this equality can be solved for the unknown term. And so we finally make the definition. So P of G on f equals P of G on f minus, like this, P of, yes, P of G minus the commutator, yes, G on f. So if P is a derivation, and this is known to me. If not, then I assume this to be known by induction. If I know how to evaluate differential operator up of degrees up to something on such fractions, then this is a rule to evaluate the next degree differential operator on similar expressions. Of course, if you think in terms of ddx and write what explicitly what's written here, you will get the familiar formula that 1 on f prime is minus f prime on f squared. No doubt about that, unless I made a mistake. So an exercise would be to show that this definition makes sense. I mean, this presentation is not unique. You can write, I don't know, gf squared or something like this. So you have to convince yourself that this really does make sense. And so we get that's our. So we've got this, and so we've got this. The claim that this is an isomorphism. The easiest way to see it is, up to this point I haven't used this. But At this point, let me use the fact that A is smooth. A smooth means that it is enough to consider a thing quickly reduced to vector fields. I leave for you to figure out all the details. I'll show you the completion of the proof in the case of differential operators of order 1. In other words, I will do it just for vector fields. Higher power of vector fields, which generate everything, as we know in a smooth case, can be done similarly. So for vector fields, what is it that we would like to show? That T sub A sub F is isomorphic to A sub F tensor A G. All right, so what's that? It's a theorem in the text by Eisenbud. A valid assumptions like, suppose omega is a module finitely presented or something like this. It's absolutely clear in the present situation when omega as well as omega A sub F is a free module. So this space is a localization of this. It's a simple exercise in commutative algebra. But this is, so that is exactly what we want. The higher powers can be done by induction similarly, and I'll leave it out. A more serious exercise. I hope I'm 100% right. This particular exercise I haven't quite done myself in all the details, although I believe that this is quite doable and as well. And if it is not, please do correct me. So exercise, you see, it is only at the last step that I used smoothness. Clearly, this is an overkill. So I verify this. Just the localization property, nothing else. Verify the localization. Verify this lemma for A, finitely generated. Perhaps, I'm not sure. I don't think it's needed. If you need an extra assumption like reduced, perhaps. But finite generation is a crucial condition. Here is another exercise. Show that this lemma fails in the case when A is the simplest possible infinitely generated polynomial ring, like C infinity. So again, in this case, of course, it's quite easy to understand what T sub A is, as well as T sub A sub F. It's absolutely clear that that's an exercise. So this algebra is not isomorphic to this one.
So right-hand side is bigger?
Yeah, right-hand side is much bigger. Yeah, you've seen it immediately, yeah.
Actually, why? I mean, any f that you localize only has involves only finitely many polynomials. So you get the impression that, whatever happens on a finite part, and then you only tensorize with some additional variables. So it's, I find it counterintuitive to assume that they are not the same.
it's that vector fields will be infinite sums. I'm suggesting a solution. It's infinite sums. So, of course, it's just sums with f's downstairs, but the power may tend to infinity. So it won't be technically
You want to put polynomial or power series?
polynomials. That's the point. The functions are polynomials, and power and vector fields will be infinite series. All right, so that's what you need, and this is something that I will note, define, assume, understandable. That what it means is that if you have even a scheme, but smooth, so smooth algebraic variety, smooth means in particular of finite type. Then there is a d sub x containing the shift of vector fields and the shift structure shift, and OX quasi right quasi coherent shift of homogeneous. And in this case, we locally, finally, having made this lengthy digression, essentially come back to an obvious picture I started with. So again, x is smooth. I pick smooth over C, so I pick a point. The C point is an honest point in x. And then x has an étal coordinate. Remembers how the axon is to be put like this or like this. Oh, which one? This? Like this or the other way? Yeah, I'm just showing my ignorance. The étal coordinate system is, there is always an étal coordinate system like this, which means, so that if you take the corresponding differentials, then at values in the fiber of the cotangent bundle at point P, that's a basis. Of the fiber, now TPX. But then you can find over some, defined over some neighborhood of this. So my x point P, and then there is a small neighborhood, so that that's my fiber. So these functions are defined over some neighborhood. Restrictions to the fiber give you a basis, and then locally you can pick a dual basis. So that the value of dxi on dk is either 0 or 1. And so that gives you trivialization of the tangent bundle. So this always exists. That's very easy to verify for people familiar with the beginnings of algebraic geometry. So what this means is that over this B is a small neighborhood, then over U are the space of sections will be more or less what I started with. So that will be an algebra freely generated by those vector fields over the functions. You will verify very easily that this condition implies that the Lie bracket, these fields pairwise commute. And the algebra is like this. And that, of course, brings us back to kind of calculus point of view on a differential operator. One last thing before I tell you something interesting. So this kind of discussion doesn't allow a Chiral analog. See, differential operator, algebra of differential operators indeed is made out of operators. The product is a composition of the operators. It's an absolutely fundamental fact. And this is what's unavailable in the general situation I'll be discussing later on. But what is available is an analog of what I'm about to say. So universal enveloping type, enveloping algebra type presentation of this subway. Again, I bring myself back to the situation of a smooth A. So remember where we started. We had A, and we had T sub A. I would like to notice that this whole thing is naturally a Lie algebra. You may argue that A isn't. It's a commutative algebra. Well, so it's an abelian. So what I'm saying is the sequence that we discussed at the beginning, A lies inside A plus T sub A. And I'm about to make a remark of absolutely obvious, but it's going to be of great importance, as you will see. I'm making the point that all these arrows respect all the structures there, and there are several. So this is a Lie algebra, and this is a, this is an algebra, and this is both Lie and A module. No, this is not quite a Lie. That's where I'm headed. So this is a Lie algebra. So in a very obvious sense of the word, this is a map of Lie algebras as well, where I will endow this with a Lie algebra structure where A, so that A is a what? Abelian ideal such that a vector field acts on an element of the algebra the way it should. The Lie bracket, I don't know, I have used this more than once, the bracket of C and A as operators acting on functions. So, because I'm getting tired, I'm just making obscure and obvious point. This is a Lie algebra. You bracket elements from A and T according to the way T acts on A. So it's totally, it's a Lie algebra in a completely tautological way. If you do so, you see that A is an abelian ideal in this algebra. And this is an exact sequence of Lie algebras and A modules, so that all the arrows respect all the structures there. Right? Anyway, the only thing I actually wanted to say at the moment is that this is a Lie algebra, so you can form the universal enveloping as a Lie algebra. I would like to compare it with, this is an associative algebra, but attached to these data is also the algebra we've just discussed. Tell me, please, is there a chance this algebra is isomorphic to this one? That's the question for graduates here. Do you want me to repeat the question? Is there a chance that this associative algebra is isomorphic to this one? They have something in common, because the Lie bracket, for example, of two vector fields is exactly as it was there. The Lie bracket of A and a vector field exactly as it is here. So they do have something in common. Can they be isomorphic? Hint, no. Why? It's not just a Lie algebra. What they have in common is hidden in the notion, in the word Lie algebra. The way they are different is hidden in the word A module. For example, the point is this thing carries lots of associative, multiplicative structure that simply, so this carries multiplicative structure that simply is not, this carries a multiplicative structure that is completely ignored by this, because that's just a universal enveloping of a Lie algebra. So for example, you can multiply two functions as functions. But this is completely different from multiplication that's defined under the aegis of universal enveloping algebra. So what I'm saying is that there is an obvious and surjective morphism of Lie algebras. Just because the bracket here is the same as there, and this is generated by A and TA. That's true. So by the universal property of the universal enveloping algebra, there is this map, and it's subjective, but there is a huge kernel. And kernel is exactly generated by the multiplicative structure that's ignored by you. So take two functions, f and g. You can multiply them as elements of the Lie algebra lying inside the universal enveloping. So this immediately kicks this element out of A. But there is another product that f and g enjoy as elements of A. And so there they are identified. So this is something that we have to get rid of. And there are two more elements of this type. You can multiply a function and the vector field. And that's the same as the vector field that lives there. I don't see any more multiplicative relations. But one relation is missing. Which one is it? What else in universal enveloping algebra is completely formal and different from its counterpart there? Unit. I told you all my units will always be identified. A is a unital algebra, but Lie algebra structure has nothing to do with that. So there is, of course, the unit element in the universal enveloping. It's kind of brought from the outside. It should be identified with the unit of A. And so if you consider the two-sided ideal generated by these elements, then think about it. It's another simple exercise. So this surjection induces an isomorphism of associative algebras. All right, having spent so much time on all of this, the question arises, why we algebraists have want to study things like that. And of course, the main example is the famous application of such objects found by typically referred to as Balancon-Bernstein localization. But of course, that the most famous result was independently obtained by Balancon-Bernstein and Kashevara and Brilinsky. And so this, let me show you. How this works. For example, so for SL2. And this is something that perhaps this is the most interesting thing I will be able to tell you, but this is also something that will be analogous to what will be found later on in the Chiral world. So we will be dealing with this group. And the Lie algebra. I guess the commutation relations are known to everybody, if not practice. So this is linked to geometry as follows. It's a very the beginning of the story in this case is very simple, but at the end it's surprisingly non-trivial, but doable. So it's people who are not quite familiar with this may enjoy figuring out some of the details here. So SL2, of course, acts on C2 by the very definition. And so SL2, therefore, acts on lines in CP2 through 0. And that's CP1. So Mike, you do have to explain exactly why the charts are as they are. All right. So this thing has two charts. And x and y are coordinates on each, and x is y inverse. So that's how, that's an explicit description of the space of lines as a variety. And if you do things, maybe make choices or something, so on 1C, so you can always make identification. So you see, SL2 acts there, and therefore the Lie algebra of SL2 maps into global sections of the tangent shape. You make some obvious choices, then on some C with coordinate x, E will be presented as minus dx, H as minus dx, minus 2x dx, and F x squared dx. So again, people who are not quite too familiar with all of this are encouraged to carry out all the necessary computation. All the information you need is on the board. The action, so you write the corresponding infinitesimal action, and if you use a concrete chart, you will get some vector fields representing those three elements. So you should get formulas like this, up to a sign. So there are some choices, but very insignificant ones. Probably some signs can be changed without doing much damage. But fundamentally, that's what you will get. Well, if so, then of course, you can consider the universal enveloping of this Lie algebra. Oh, by the way, I have never defined it, Mayuki. Is this a crime? That's fine, all right. So then, of course, automatically, vector fields, well, in this case, vector fields locally generate everything as we discussed, but in any case, if you have a vector field, then you get, by multiplying them, you'll get elements of global differential operators. And of course, this map gives you the map of universal enveloping to the global sections of the algebra of differential operators. Question. Is this an isomorphism? If you don't know the answer, you won't be able. It's not a question. It's not something I can ask you honestly. The answer is no, but the reason for this answer is it's not obvious. You have to compute something. If you do, then you can check. This element, and I'm pretending that nobody knows it, goes to 0. Now, of course, it's something like this. You see, this is this is an associative algebra morphism. That's obvious. So an element going to 0 has some fundamental consequences. It's an ideal that can go to 0. So if element goes to 0, there's something special about it. Of course, everybody knows what's special about that element. It's no use pretending. It's a central element. In fact, it generates the center of the universal enveloping algebra. And again, people who there's something fundamental. If you haven't never heard about it, try to study this. So you can verify that the bracket of any element of SL2 with this famous element is 0, which means that this element, let me call it C, I don't know. So C is SL2 invariant, and being SL2 invariant is the same as being central. And so that morphism factors through the morphism of the algebra mod out its ideal generated by the center. The same question remains, is this an isomorphism? An isomorphism. Yes, it is. Again? Yes, certainly, yes. So,
one end, generally one end.
Yeah, so everything is graded. the thing looks like a polynomial ring. So you have to take z plus means the direct sum of all components of z of degree greater than 1. So augmentation is more, better to say like this. So there is a map from this to C, and you take the kernel, and z plus is the intersection of this with the kernel of that map. So if you send 1 to 0, then you're done for. Don't do that. Thank you. A theorem. This is an isomorphism, and this theorem is an important part of this general program of Bernstein-Beilinson localization. It's great fun and very instructive to prove it, and so I'll do this for you. It's a good exercise on things that we studied. And so in this particular case, this is an example of how you can compute sometimes the algebra of globally defined differential operators. So in this case, you see that it has a rather profound meaning in terms of the corresponding universal enveloping algebra. So proof. All right, so here is a map of algebras. You will immediately see that both algebras are filtered. And in a similar way, U of G, probably, remember we talked about quantization. Probably I should have shown you this example at that time. U of G is a quantization of the symmetric algebra on G. So the filtration is given by assigning to an element of G degree 1. It's not naturally a grading, but rather a filtration of the algebra, just because the bracket of two elements of degree 1 is not an element of degree 1, but rather an element of degree degree of 1 and 1 will be not 2, but 1. So it's a filtration. That algebra on the right is also filtered, as we discussed, just because the shift D is. And therefore, you compare the two definitions of filtration and see that this map respects it. So we get the map of filtered components. So U, I, SO2, gamma, DI, CP1. So you quotient out by U to I minus 1. You get SI. So it goes to gamma. DI mod out gamma of DI minus 1. This map, of course, is induced by the obvious embedding of sheaves. And this, as we discussed, is precisely the I symmetric power of the tangent sheaf. So if you take the map, if you apply the function of global sections, you will see that this maps onto the globe, not onto, it's the homological algebra starts. But there is a map like this. The I, yeah. So we have this composite map. Agreed? Now, we will verify two statements. First, this composite map is an isomorphism. And second, there is a natural isomorphism of, as vector spaces, of the global sections of globally defined differential operators, and the global sections, the space of global sections of the symmetric algebra. Agreed? So, if this, for any I, is isomorphic to this, then the direct sum of those, which is the graded object, is isomorphic to the direct sum of these.
You mean
Therefore, to this.
you have the quotient of the center. Casimir powers.
That's what I meant. Ah, I forgot to introduce the notation. It's U0.
Okay.
So then this, yeah. So this, thank you for, yeah. So I'll have to be careful. So this is the ith graded component of U0. Yeah. So its description is not that obvious, and this is somehow the point. It's not quite a polynomial, not a polynomial. Now, you see, it's a standard argument. How do you identify two vector spaces? So if both are filtered, and the map of the graded spaces is an isomorphism, then the map of spaces themselves is an isomorphism. And this is what's achieved by the concatenation of items 1 and 2. So item 1 will show you that the graded algebra, so item 1 will imply that the graded algebra, graded object of this U0 is isomorphic to this, so that's what's written. And then the second item will identify it with this. Not as an algebra, but as a vector space. But since by construction the map itself is a morphism of algebras, then the algebras are automatically isomorphic. Agreed? Any questions? Yeah, that, you know, I'm talking to graduates. When you become professor, you'll know how disconcerting it is to encounter silences like this. It's like, you know, you want to go out and commit suicide right away. It looks like I'm wasting your time completely. Are you lost? Or is everything clear, really? Or complain to Tomayuki later on, and he will tell me I'm sure.
I have a question. Why do you do it this way? It seems to me that assertion 2 is much easier to prove directly than
Yeah, that's what I will do. 2 is very simple, exactly. That was my phrase.
so
1 is harder, but that's the fun part. The combination will give us the result. I'm not proving 2. I'm using 2 to prove the result. Again, the scheme is this. You have a map of algebras. You want to prove it, there is an isomorphism. A typical argument is if they are filtered, then you go over to the map of graded spaces. If this is an isomorphism, then the initial map is an isomorphism of vector spaces automatically. But since this is a morphism of algebras, then this is automatically an isomorphism of algebras. Because there is an inverse, and therefore it's automatically also a morphism. All right, so just, of course, people who know algebraic geometry immediately see that item 2 is very simple. But for those beginning to study algebraic geometry in conjunction with, you know, some Lie algebra, It's a very good exercise. So I will sketch it. So 2, I'll do it very briefly. So this is all about what I started with. So this is, by definition, this is an exact sequence of shapes. So it gives you an exact sequence of, not exact, but the beginning of a long exact sequence of the homology. So the next will be the first homology. What was it? DI minus 1. Of course, the argument will be inductive. And the point of the argument is that for each I, this is 0. And that's what, so if you have this for all i's, then that's exactly what item 2 claims. So why is it? That's because everybody knows what this is. That's CP1 enjoys a family of CPN, but in the case of CP1 it's especially easy. So there's a family of shapes. ON is the one for which the gluing functions on the intersection are you have x, y, and you have these are shapes of rank 1 free O modules. And ON is obtained if S0 equals S1 times y to the n. So if n is positive, such things tend to have global sections. And the point of which discussion is that Si is precisely O to I. So for example, the vector field is O2. And this particular example is very easy to do. It's just, you know, the chain rule. So you have ddx on one chart. So why is that? Well, this is generated by ddx on the x chart and ddy on the y chart. And x equals y inverse. So you immediately see that dy is, I guess, minus x squared dx. Yeah, well, overall sign is not a big deal. In general, you write the nth power. So you will have x to 2 times n. You immediately see, by the way, the difference between the symmetric power and the differential operators. If you raise to power n the actual vector field, then the result will be like this only for C minus student. X and ddx don't commute, but they do in the symmetric algebra. And so the nth power will be transformed like this. So this is not true for the order n differential operator written here, but it is true for a section of this shape. And then a similar computable, so you see dx to the nth extends to a global section. And then if you play a little bit, you will see that you can multiply it by some powers of x, and you will still be getting global sections up to the point. And I guess the last one, when it will work, will be x to the n, something like this. 2n. Yeah, I think 2n. If n is 1, there will be ddx, x ddx, and x squared ddx. That could have been easy to predict. I'm claiming that in this particular case, the space of global sections is at least three-dimensional. Why is that? It's obvious, because we discussed that up to a sign, these are images of elements of SL2. And those, by definition, are globally defined. So, and then a simple computation will show you that for this shift there is nothing else. And the same computation will show you that for the nth power. And I don't have to write Sn, it's a rank 1 shift, so I simply write like this. That's the space of global sections. On the other hand, so that's gamma. On the other hand, it's also a standard exercise in linear algebra is that H1 is 0 if n is positive, even non-negative. And so this is 0 if I is, I don't know, if I is 1, this is can be verified by hands, and then you use induction, and we're done. That makes sense. So for shifts like this, higher cohomology vanish, and by induction, the whole thing is made out of such things, and everything splits upon the passage to the graded space, and we get an isomorphism. And that's exactly what item 2 claims. Right? If there are questions, ask me next. Ask me after the lecture or before the next one. I'll be happy to elaborate. So item 2 really is a very simple exercise. Item 1 is, that's where the fun begins. Item 1 is a very nice exercise in representation theory. Let me explain. So what's written there? So I have the graded object. It's convenient to consider all of them. So the graded object associated to U sub 0 of SL2. And it maps to the direct sum of spaces of global sections of X, CP1, power CP1. I should have written again the nth symmetric power, but since this is rank 1, I can as well write just T to the n. Doesn't matter. What matters is that this is O2 times n. So we want to show that this is an isomorphism. This is an exercise in representation theory. How does the representation theory enter the game? Well, this is not just a map of vector spaces. This is a map of SL2 modules. Where SL2 acts on both sides in a similar way. What do you think it is? So we need an action that doesn't change the power n. It should preserve. There is only one way of doing this. Here you could try to multiply on the left and on the right, but neither of these possibilities make sense because that changes the degree. What you need is the adjoint action. So here the action is adjoint. There is such an action on elements of the universal enveloping. You take an element of SL2, an element of the universal enveloping, and you grab it. it descends to the graded. Of course, it respects the quotienting out of the center, and so it gives you the action there. What do you think the action here is? It's similar. As such, there is only one way of defining it. So, for example, we would like to have an action of SL2 on a globally defined vector field. How can SL2 operate on globally defined vector fields? SL2 itself is a vector. There is a map of SL2 to globally defined vector fields. And then it acts here by the Lie bracket. So, informally speaking, the action is by the Lie bracket. So essentially just as it was done here, except that if you think of elements of SL2 as globally defined vector field, then you think of elements of the graded space as products of space. And here, it's more or less the same thing is done, but honestly, there we can just think of them as globally defined vector fields. Here we're dealing with actual globally defined vector fields. Make sense? The very construction shows that the map is a morphism of SL2 modules. All right, so that makes our life much easier. It's not just a map of vector spaces, but SL2 modules. So we can use the presentation theory of SL2. That's great. So what are both sides as SL2 modules? The right-hand side we actually have just discussed. I haven't used the word SL2 module, but as vector spaces, we discussed them. I probably have to make a digression. I believe everybody knows that, but I need to introduce the notation. So for SL2, for each M, there is a unique, irreducible representation. I'll call it, I don't know, L of M of dimension M plus 1 and of highest weight in M. Highest weight means an element V such that EV is 0, HV is M V. We discussed the space. It was so what were the generators? dx, ddx to the n, x, ddx to the n, etc. I believe x to the 2 times n ddx. So at least, yeah, so you would expect this to be L. L to n. And it is easy to verify that this indeed is direct sum of L to 2 times n. The easiest way to see it is to observe that this thing is indeed highest weight vector of weight 2 times n. Of course, it's killed by ddx. How else can it behave with respect to ddx? And then x ddx, which is h minus x ddh, you can easily commute with it and get the 2 times nx. The only trouble being to getting the sign right. Since this is finite dimensional, it should be positive, and so no doubt about it. All right, so the story is concluded by the following famous theorem of constant. Let me state it. So, of course, constant proved it for an arbitrary simple algebra. And in general, it's a much more complicated result. But in the case of SL2, the structure of this thing is a joint, as an SL2 module with respect to the joint action, is easy to guess and then prove that the guess is correct. So what can we say? There are elements, 1, e squared, e to the n. They are all, so e to the nth is highest weight vector of weight 2 times n. Therefore, it automatically generates a L of 2 times n living inside the result. What else is there? Well, definitely, this cannot be everything, because that gives you only one trivial, almost, let me ask you a question, or is it too late for silly questions? Can U of SL2 be the direct sum of these modules? Is there a chance that U of SL2 is a direct sum of modules like this? There is another trivial representation, and I explained why. There is one, so that gives you C. Of course, it's a trivial. One gives you a trivial representation of SL2 because one commutes with everything, so that's trivial. There is a trivial representation that's not on the limit. None of these is trivial because the highest weight is non-zero. There is another one. Oh, come. Casimir, it's a central element, also gives you trivial representation. So then, of course, you can have at least powers of it will be all trivial. So there is, of course, the polynomial algebra in one variable. You just identify this variable with this element. And this whole algebra lies inside SL2. Then there is, of course, a direct, so each e to the n gives you L2 to the n. So there is obviously a map. If you have one such module, e to the n, generated by e to the n, then applying any polynomial in this, multiplying this by any polynomial in those, you'll get another element of U of SL2, and it will always also be such an element, so such a module. So these modules enter the whole algebra with infinite multiplicities. And at least there is one for each element of this polynomial ring. And so there is a map from this space to the universal enveloping of SL2. Can there be a kernel? It's easy to figure out that there cannot. This is an embedding. That's essentially the complete reducibility result. Of course, you can easily verify that these elements multiplied by polynomials like that are all linearly independent. And those modules cannot intersect because of complete reducibility. So there is this embedding. Constant's theorem claims that this actually is an isomorphism. So exercise will be to verify it, but I'll tell you how. There is a simple way of doing this. Of course, this is peculiar to the simple description of high weights. I don't believe such a simple description is available for other Lie algebras. But once you have this, in the case of SL2, another simplification occurs. You can prove that this is an isomorphism by comparing the characters of these spaces. So hint. You know, if you have a bigraded vector space, then you can define its character by simply, if those are finite dimensional, by simply in the standard. You can apply the same thing to USL2. I'll write the formula and then I'll briefly discuss it so that you will see that the formula makes sense, obvious. So the character of the universal enveloping is 1 divided by 1 minus x squared t, 1 minus t, and 1 minus x to the minus second. Is it clear how I make sense out of this as a formal power series like this? I just use the geometric series formula for each of these fractions. So for example, 1 divided by 1 minus x squared t is understood as the sum x to the 2 times n t to the n. And you can multiply such things by expanding out formula. No problem with that. So why does this make sense? So what do x and t measure? These 2 and minus 2 give you a hint that these have to do with eigenvalues of h. So x counts, so to say, the eigenvalues of h. H, remember, H is a diagonal matrix. Its bracket with E is 2 times n, with F is minus 2 times F. And that's the grading I'm talking about. So H assigns to E 2 and to F minus 2. That's my 2 and minus 2 here. Remember, universal enveloping by its size is like the polynomial ring. So there will be 3 variables, E, F, and H. So this apparently has to do with E, this has to do with F, and this with H. The real T is just a statement of the fact that degree of each of them is 1. X squared says that its eigenvalue with respect to the joint action of H is 2. And it's minus 2 is a similar statement for F. This thing is also graded. And what remains is comparison of the grading. So it really is a simple combinatorial problem of the kind, I guess, Boris is teaching right now, Barry Fagan is teaching right now here. So start expanding out and compute the multiplicities, and then compare with these. So for example, that's clear. That's from the point of view of that computation, each of them is just t squared. The overall degree is 0. And this is totally different. This is, for each n, you will have what? E to the n, so it's t to the n. And then the character of this module would be e to the 2n plus 1. No, it's not e. Isn't it? So the character which summoned will be x to the 2n plus 1 minus x to the minus 2n minus 1 divided by x minus x input. It's written as a fraction, but I shouldn't. Let me extend this out. So x to the 2 times n plus x to the 2 times n minus 2 plus etc. X to the minus 2 times n. So you have in front of you two formal power series in Laurent in X and polynomial in T. It's a nice combinatorial problem to see that the characters are the same. Therefore, vector spaces are isomorphic. I'm almost done. That proves, of course, that result because this constant is a result for the entire U of SL2. What happens is we have passed the U of 0, which means that polynomials in Casimir are killed. And the only thing that's left is this. That survives. And that's exactly what's written on the right. Hence, an isomorphism. And the theorem is proved. All right, I've just run out of time. I'll tell you if you, I'm almost done with Beilinson-Bernstein localization, but it will take me some time to finish it, more than 2 minutes that I have, so I'll stop now and finish tomorrow. I would be surprised if there were any questions now.
About general symbol, general plan, right?
The proof has the same structure, some algebraic geometry, some representation theory, but both are way. Yeah, this is true in general. It can be generalized, and even for SL2, this must be generalized, and I will explain how. You have to pass from differential operators to twisted differential operators. So even for SL2, this is not the end of the story. But then you can go from SL2 to an arbitrary simple G. And the same thing is true, and the proof has the same structure, but it is immensely more complicated. But both items 1 and 2 survive, so the structure of the proof is similar. You first identify.
So this left-hand side also cushion out the Casimir including high degree.
Everything is valid, but it's much more complicated. Also, the crucial result is Kostan's theorem, but it appears as a statement about functions on the Nilpotent cone.